Hi, I'm Lauren Chanen, and for my, oh, what? Are you starting the timer?
Yeah, we're actually ahead of time. You
Oh,
have a minute.
okay.
I'll introduce you.
Oh, great.
I like the enthusiasm though.
I'm ready for it.
All right. Our next speaker is Lauren Chanen. Go ahead, Lauren.
Okay, for my thesis project, I designed and constructed a drop weight impact testing system for the purpose of characterizing soft materials. In this presentation, I will talk about the background and significance of the project and why we decided to undertake this project. I will go over the overall concept of the system and then go into further detail on the system in terms of theory, design and utilization, and validation, including some results. And then I will touch upon my conclusions. So the soft materials that this system was designed to study are specifically elastomeric foams, which are extremely useful in impact protection applications due to their ability to dissipate great amounts of energy while also being soft and lightweight. So they're used in applications such as helmets or phone cases, many other products. But yet we still don't have an adequate model for their time-dependent mechanical deformation at a wide range of strain rates. And typical impacts occur at a strain rate range from 10 to the negative third to 10 to the fourth 1/seconds for nominal compressive strains between 25 and 75%. So as shown in the diagram on the right, there are certain impact testing methods for certain ranges of strain rates. But before my system, there was a gap in strain rate capabilities. So the red box represents the drop weight impact testing system, and that fills a gap in capabilities between 10 to the first to 10 to the third 1/seconds. So this will allow researchers to characterize these materials at the complete range of strain rates. So the overall concept of the system is that a gravity-driven striker bar drops through a tube to impact the sample below. A load cell underneath the sample obtains voltage versus time data, which can be converted easily using a conversion factor into force versus time data. A high-speed camera takes photos of the sample as it undergoes the impact in order to analyze the strain using digital image correlation. It's really important that researchers can actually see what's happening to the sample during the impact so that they know that it was a compressive stress as intended rather than a shear stress, which could happen if something is misoriented, in which case the researcher should obtain new data. So in order to determine what kinds of striker bars and drop heights were needed to get the strain rates and strains that we desired to study, I had to start to understand the system. So on the top left, there's a diagram with a small portion of the striker bar and a force balance on it. So using this simple force balance, combined with the assumption that the materials were homogeneous, isotropic, linearly elastic materials, I derived the 1D wave equation. All the equations below came from the 1D wave equation and were used to determine the striker bars for desired strains and strain rates. Clearly, there are a lot of variables in these equations, so I needed to set some constraints. So the Frank lab has already studied a similar elastomeric foam, so I kind of used that as a guiding point for the system that this foam would be similar to other foams studied. So we knew the length, the thickness of this foam and an approximate Young's modulus. And also because the foam is available in sheets, we simplified calculations by assuming that the area of the striker bar and the area of the sample were equal. Then I already mentioned the strain and strain rate ranges we desired to study. 25 to 75% nominal compressive strain for strain rates from 10 to the first to 10 to the third 1/seconds. So using all of this information, I got combinations of drop bars and drop heights to use for the desired strain and strain rate combinations. And in my testing, I utilized the 2 bars in the blue box. But the overall greatest height needed was 18.44 feet. That's the drop height plus the length of the bar. So the system was designed to reach approximately 20 feet. Therefore, it needed to be located in Print's lab to accommodate this height. Because it was in Print's lab, there are certain considerations that had to be made. First of all, it needed to be built without a ladder for safety reasons, and it needed to be able to be lowered down so that the crane that's used in Print's lab wouldn't be obstructed. So it's a telescoping design that utilizes 4 box components nested within each other and raised one at a time using a pulley and winch assembly. That's shown here, the pulley and winch assembly. Once one box is raised, it's connected into place and the next is then raised. So at the lowered height, it's approximately 6 feet tall and could approximately go up to 20 feet tall. Here's a partially raised photo. So each time that a box is raised, a PVC tube is placed so that there will be one long PVC tube composed of several segments, but one long tube running through the center for the striker bars to drop through. When a researcher is utilizing the system, there are three components to utilization. The release mechanism, which is simply a fishing line hoist connected on an eye bolt to the striker bar, the load cell, which obtains force versus time data, and the high-speed camera used to analyze strain. Next, I wanted to validate the system by comparing the impact velocity, the theoretical and experimental impact velocities. So as mentioned, the load cell gave me force versus time data, and using Newton's second law and the mass of the striker bar, it was easy to convert this data to acceleration versus time. Then, using the conservation of momentum, I got this first equation here, which allows me to calculate the experimental impact velocity by integrating the curve from the beginning of the impact to the end of the impact. That was the acceleration curve that I integrated. So the potential energy equation was used to give me the theoretical impact velocity equation as shown, v equals square root 2 gh. It's just dependent upon the drop height. So I compared the experimental impact velocity and theoretical impact velocity using this data here, which was for a plastic bar, ultra high weight molecular polyethylene. So the full data set is shown on the left, where the bar drops and then bounces several times with decreasing force each time until it just sits on the load cell. And then the one on the right shows the data set cropped just for the first impact. In my test, I didn't have a sample. I just had the striker bar impacting the load cell directly for validation purposes. So I got the experimental impact velocity using this curve to be 5.45 meters per second, compared with the theoretical 5.859 meters per second. Thus, I had only a 7% error. I wanted to know, though, how repeatable this data would be. So I ran that same test several times with that impact bar at that drop height, and then another impact bar at the same drop height, and overlaid the data sets as shown. And they're not exactly perfect, but they follow the same trends, so I felt that the system had some repeatability and consistency. And in addition, I got relatively the same impact velocity for the second bar dropped from the same height. I got 5.236 meters per second, which is approximately a 10% error. I felt that this error was probably due to resistance experienced by the striker bar as it maybe made contact with the tube as it dropped, maybe some resistance in the fishing line it was connected to, or air resistance. So this error made sense to me, and I felt that the conservation of momentum was validated. Next, I wanted to observe the 1D stress waves in the system by comparing the theoretical and experimental impact times. The theoretical impact time, as shown in the equation above, was derived using the 1D wave equation that I showed earlier. And the experimental impact time was estimated visually on the plot as shown by that delta t on the diagram. So I got a theoretical impact time for this particular bar to be 0.49 milliseconds, and the experimental was much larger at 0.1 seconds. Clearly, these two values do not line up, so that led me to believe that my assumption that they were homogeneous, isotropic, linearly elastic materials was not valid and did not hold. So in conclusion, I had a validation from the linear momentum balance from the way that the impact velocities matched up with little error, and the system will be utilized by researchers using high-speed videography as mentioned, but yet we still have this discrepancy in impact times. So there are several reasons for that. The material is probably non-linearly elastic or not fully elastic. We've seen that this 1D analysis works well for metal bars and has been used in that way, but maybe it doesn't work as well for plastic bars due to the energy dissipation. And in addition, the Young's modulus values I used to calculate the theoretical impact time were quasi-statically determined, but they may have been different in this case because there were high impact rates, so it could have changed the Young's modulus due to stiffening or softening of the material. So moving forward with the modified 1D stress waves happening in the system, it will be more difficult for researchers to predict like a striker bar and drop height combination to give a desired strain and strain rate. They can attempt to get an idea for the strain rate that an impact bar will cause by back calculating an effective Young's modulus using an experimental impact time. And with that Young's modulus, they can get the wave speed and then calculate the strain rate. But again, this would utilize the 1D wave equations, so it wouldn't be perfectly accurate, but may give them a closer idea of the strain rate. So they will, in the future, need more sophisticated equations to analyze this, maybe hyperelastic or viscoelastic material equations in order to predict the strain rate that will happen from a given bar. But in general, they can still utilize the system along with a high-speed camera to obtain data that they can analyze the strain using digital image correlation. So I would like to thank my advisor, Professor Frank, and my reader, Professor Hennen, and also Charlie Vickers and Brian Corkum that you've probably seen and met in Prince Lab. They were very helpful. So thank you. Any questions? Any questions? Yeah.
Were there benefits of using plastic striker bars as opposed to the metal bars?
Well, because the material to be studied are these really soft materials, to get the desired strain and strain rate, you need a bar of a certain material characteristics. A metal bar could be used, but it would probably give such like a harsh strain, a high strain and high strain rate that it wasn't in the range of what we desired to study. Anything else? Okay, thank you.
Sorry.
That's okay.